Hey everyone, so I want to talk about the last thing dealing with conservation of energy, and that's the energy graphs. So this is something that this video is going to be a little bit different because there's no real question, but this is something that you're going to need to be able to do is know how all the different forms of energy relate to different variables. So let's consider the case where an object's thrown into the air. We want to be able to make a graph of the potential energy versus height, the kinetic energy versus velocity, kinetic energy versus height, potential energy versus kinetic energy, potential energy versus time, kinetic energy versus time, and total energy versus time. Some of these are easier than others. What I want you to try to do is try and see if you can actually set these up yourself. Try to think about what the relationship looks like. I will point out that for the most part, the graph should either be linear or curved in some way. All right, so those are the two choices. There shouldn't be any like weird, awkward shapes. It should be either an exponential curve, a decay curve, or a linear graph. So try this out. You can pause the video, work stuff, and we'll go over in a second. All right. So for potential energy and height, that one's actually really easy. Uh, Based straight on the equation, potential energy equals mgh. So that's a direct relationship, which means that we should have a linear line. And the next one's also easy, kinetic energy and velocity. Again, right from the equation, we can see that they have an exponential relationship because that there's a square on that v. So if I graph kinetic energy versus velocity, I should get a curve. Now this is where it starts getting a little bit different because now we're going to have to try to compare variables that aren't really related to each other in strict equations. So what we're going to want to do is try to work around with the equations until we can get a way of, setting them equal so that we can have a relationship between them. All right, so for example, here. Now, because of conservation energy, I should have actually changed this to be delta K equals to negative delta U, because the amount that the kinetic energy changes by is equal to the amount that the potential energy changes by. So if potential energy increases by 50, kinetic energy is going to decrease by 50. Because of this relationship, I can see that kinetic energy equals mgh. So K is going to be directly proportional to h. But because this negative is here, that means that as the height increases, the kinetic energy is going to decrease. So it's going to look like this. It's going to be a linear line from there. So realistically, what we're basically saying is that since kinetic energy and potential are directly related, because of conservation of energy, when one goes up, the other one goes down, and because potential energy are directly related to height, then we know that kinetic energy and height have to be directly proportional, but with this downward slope rather than an upward slope. Right? This kind of goes back to what I did before. That potential energy and kinetic energy are, again, negatively proportional. That when one goes up, the other one goes down. Again, I should have had deltas in here. Um, Now, this one is going to be a little bit hard to see as I showed here, but for the potential energy versus time. So this goes to where we're going to have to actually think about how height is related to time. And that's actually going to be the easier case to do. So if we throw an object up into the air, we know that the vertical position as a function of time is going to follow a parabolic curve because that's what's going on in the vertical direction. It's got a vertical velocity going upwards, and it's got a negative acceleration going down. So the slope will slowly decrease to zero until the graph starts coming back down, and the slope starts increasing in the negative direction. So because the height and the time have this curved relationship, that means potential energy and time also have to have that same curved relationship. Again, notice how we're doing this, that we're looking at it and say, okay, well, U is proportional to H. So if I want to find the relationship between U and T, maybe it'd be easier to look at U and well, look at H and T. So because of the equation, x equals one half one half at squared. We can see again that the vertical height, I should probably have made this a y, the vertical height and the time squared, or the time, are have this exponential relationship, but curved in this specific way. All right. Now, mechanical energy versus time is easy. Again, mechanical energy never changes since this is not the uh, what's the phrase? This is not a case where energy is being lost to friction. So the mechanical energy is conserved. Note, mechanical energy does not have to be conserved. It's only conserved in this case because, again, it's an ideal situation. Now, with this and the potential energy looking like this, I can use this to figure out what the kinetic energy is. Because in a case like this, we have mechanical energy being equal to the, oh, sorry, the potential plus kinetic. So at this initial location, the potential energy is zero, which means that if the mechanical energy is, I know I love using this number, but 50 joules, then the kinetic energy has to be 50 joules. So my kinetic energy at this point, at the beginning, is going to be here. If I look at this point, I didn't have it cross, but let's say this ends up going and equaling 50 joules. Well, now we have the opposite case where the mechanical energy and the potential are equal to each other. So that means that kinetic energy has to be zero. And I could do this for all these different points, and it turns out that my kinetic energy will actually be curved like this. Uh, that's pretty much what we're doing. Another way of putting it, if you didn't know about that, um, we could have also used a very similar relationship that we did before. That since kinetic energy was proportional, or was proportional to potential, but like in the negative case, then since potential was proportional to t squared, we know that the kinetic energy is going to be proportional to t squared as well, and be flipped because of that inverse relationship, not inverse, but that flipped relationship, that negative relationship between kinetic and potential. This is actually a very common graph that you might see where you have kinetic energy and potential kind of overlaid on top of each other, and then mechanical energy putting on top to kind of show that, if I took any 2 points and added the potential and kinetic at that location, I should be getting the same mechanical energy throughout. So if I add this point and this point, I should get this point. If I add these 2 points together, I should get this point. If I add this and this, I should get this, and so on and so on. Any 2 points that I add in a straight line should add up to the mechanical energy. And that's pretty much it with this. Like I said, you should be able to know how these graphs come about. Uh, Even though I gave you an idea of how the graphs look based off of a scenario, note that these graphs look like this strictly because of the scenario that I presented, that the ball was being thrown up to some height. If I slightly change that scenario, maybe I make it so that there's energy being lost as it goes up. Maybe instead of it being thrown up, it's now being thrown down. These graphs are going to change. They may have a similar shape throughout the whole process, but they are going to change in some way. So you want to know how these graphs came about. So try to make sure that you kind of review what I had mentioned, and how you're supposed to go through the thought process to figure out what these energy graphs are going to look like. That's it for conservation of energy. The last thing that we need to do is we're going to talk about spring energy. And for the most part, that's just me adding in a little bit of extra information for springs. Nothing too crazy, but I will point out that a lot of the questions that you're going to see when it comes to spring energy are pretty much going to be uh, it's just going to be another type of potential. So it's not like you're really thinking too much about it. So you will watch that video in the next time. So if you have any questions, feel free to let me know. Otherwise, good luck and have a great day.